For starters, I would like to see a show of hands. Who of you guys, this will be very surprising, uses Java 8 in production? I'm shocked. Another show of hands. Who of you uses a version of Java older than Java 8 in production? Now I'm impressed. And this is the moment where you can impress me even more still. Who of you guys, this will be a shock for you in turn, uses a version of Java newer, fresher, younger than Java 8 in production? Kinda jealous. And also not completely unexpected. With that, as you all are perfectly aware, one of the greater, nobler aspects of our profession is reusability. So in that manner, I decided to reuse this presentation, or at least parts of it, and I'm going to talk about what's new in the Java ecosystem, in the JDK ecosystem. Aside for the subjects I talked about a year ago, if you are interested in them, and if you actually saw the presentation, you theoretically at least should know the answer to the question, by the way, that's asked today, then I recommend you watching the video on YouTube, which was recorded like 2 days. Or if you prefer so for some reason, you can also watch someone competent instead of me talking about the same subjects, which I recommend because the subjects are that the growth development of Java is fascinating. And I'll skim over just quickly what I've talked about the previous year and what I'm going to talk about this year. Also a quick disclaimer, I know I'm weird in this regard, really like this programming language, so despite whatever you're going to hear tonight, please take that into account, because the problem is that I'm going to be talking about the less pleasant, less pleasurable aspects of coding working daily with Java, by essence, because I'm going to talk about what's going to be changed, fixed about the language. So if it's going to be fixed, then it has to, by definition, not to work very well as it is. So, without further ado, there are currently 5 very big ongoing projects in the growth development of the Java language, Java platform. The one that has the most fireworks is certainly Project Amber. It's kind of the impressive low-hanging fruit, and that's the one I talked last year. And that's the one I recommend full-heartedly for you to investigate, because parts of it are already in the language. That's why I asked in the beginning who uses which version of the language currently on production, because part of what Project Amber set out to deliver is already delivered. And by the way, we have currently Java 11, if you were wondering. So in Java 11. And the more impressive parts still are going to be delivered in the next version of Java, Java 12, which is coming in half a year. Project Valhalla is actually going to be the main focus of this presentation, so I'm not going to describe it now. Project Panama, in turn, is supposed to deliver a better and more elegant alternative to GINI. In terms of connectivity with native C code, and it's going actually rather well. And Project Metropolis is very ambitious in the regard that it envisions to bring Java on Java. So Java is meant to be compiled by Graal, which is written almost completely in Java, and that is a completely different, very ambitious malware. Just if you haven't heard about Graal, it envisions as an ahead-of-time compiler to compile code, polylinguistic. God, that's a tongue twister. Code performantly, and that is also going actually surprisingly not. So on to Project Valhalla and Project Loom. Those are the details of Amber. We already have variable type inference. We will have pattern matching in the next version of the language in half a year, and that's actually very impressive. And data classes probably in the next version after that. What I will actually want to talk about first today, though, before we dive into the mini details, is something that was announced not so far ago, a few months back, and something that we will get in the next version of the language, which are raw strings that probably quite a lot of you guys already know from different programming languages, and they couldn't come sooner, I guess, because it's not like we were waiting 20 years for those. And I'm not going to go into the details. This is considered as kind of a commercial, I guess, advertisement for some neat toys that we're getting in the near future. Just bask in the glory of the snippets that I'm going to show you now. This isn't really a very convincing example of how raw strings work, because it works on the assumption that you use Windows paths, and as we know, there are no real Java developers who use Windows, right? Basically, what the two most important, again, without going into details, properties of raw strings are that they are multi-line. They don't have to end in the line that they began. And the second most important property is that they ignore all asterisk. That's not exactly true. Escape characters. And the second quality is important here. We all know what kind of hell. By the way, please notice the new delimitation character for raw strings, which is a tick. That's not a single quote that you see in the line below. It's a tick. That's the character you have in the top left corner of your keyboards. We all know what hell on earth it is to use raw string to write regular expressions in Java. This will actually make it considerably easier, which you can already see by this oversimplified example. And we achieved that by, once again, ignoring escape characters, which is a nightmare when you are using strings to write regular expressions in our beloved programming language. Moving on, here we see the multi-line capacity. I'll just give you a moment to bask in the glory of not having to write, not having to manually end each line, and not having to manually remember about concatenating the strings. The aspect of how this is translated to I'm actually at the loss of words. Indentations, yeah. how this is translated to indentations is actually slightly more complicated. I'm not going to talk about that, but there are going to be library functions for that. And here we have another nightmarish scenario for Java developers using the old string implementation, which is embedding pretty much any other programming language nesting, pretty much any other programming language inside of Java code. As you can see on the provided snippet, the bottom example is far more readable and far clearer, or at least I would say so. And that's just a brief demo so that you guys know what's in store for you in the close future. If you upgrade from that Java 8, that is, probably in the next 10 years, hopefully. And now to the, well, more, I would say, at least for me personally, painful. This is probably actually, from my personal standpoint, the most painful part of the whole experience of working with Java, and thankfully that is going to be fixed. Well, maybe not in the near future, but it's coming. So first, a philosophical question. What's more important? Is it a more graceful design, a better abstraction, or is it the performance of the code? And quite a lot of you probably at this very moment have this famous quote in your heads. So I'm not going to prolong anymore, and I'm going to simply spill it out. And Sir, one of the greater programmers of our time, Donald Knuth, made this famous statement that premature optimization is the root of all evil. And that is the most general answer to that question. And, well, I believe that we as an industry, me personally, and probably the vast majority of you by now instinctively agree with this quote. However, as some of you with probably better eyesight, because I didn't manage to properly widen the rest of the text out, managed to see, this quote is ridiculously put out of context, which is, we should forget about small efficiencies, say about, and this is the key part, 97% of the time, premature optimization is the root of all evil. Yet, we should not pass up our opportunities and that critical 3%. And so, well, that again seems all fine and well. No controversies here, but this brings us to the obvious problem, and it brings us to the obvious question: how do we take apart those critical 3% from those non-critical 97%? How do we define our critical path? And I'm not asking you for specific solutions, specific implementations to that problem, because there are some, in fact, as we all perfectly are aware of. It's not undoable. It usually simply happens too late after we already shipped our code to production. However, it is perfectly doable. It just requires effort. And here we arrive at the, again, philosophical question. Well, we do have to put in that effort. And quite often it's by every length and a completely untrivial effort to undertake. So by being in this position of actually having to think about this problem, we are putting in, by definition, huge amounts of effort that we could put elsewhere. So if the job of the programming language, basically, should be to avoid such situations as much as possible. It can't ignore them altogether, that's impossible, but it should ignore them as much. It should eliminate such situations as much as possible. A good example would be Kotlin, which really strives in this direction. The problem with modern Java, well, less modern especially, is that it generates such problems quite often. It puts us in that situation. We actually have to consider situations where good code is less performant than bad code. And it doesn't need to be like that. It doesn't need to be like that always. There are situations in Java where if we change the language somewhat in some aspects, by writing code that's clean, code that's elegant, code that's graceful, you would naturally go in the direction of writing performant code. And what is a good situation of this dilemma? Well, this is actually quite dreadful. We don't really think about this on a daily basis. We kind of numb ourselves to it. But this capital L in long, the capital I in integer, in list of integer, if in any generic of a type that should be instinctively a primitive, carries with itself a huge performance penalty that in the vast majority of cases we simply have no choice but we pay. And when you think about it, the fact that we are unable, because of the current implementation of the generic system in Java, of using a primitive in this place, in this spot, in such a performance-critical aspect of the programming language, of the library that backs it up, the price is so humongous and paid on such a daily basis that it's better not to think about it, really. Basically, in case it wasn't perfectly clear by now, as it stands, the generic implementation of the language doesn't allow you to use primitives in collections or in fact in any kind of generics. So the obvious solution to this problem would be to allow us obviously to use primitives, right? But here lies a deeper question actually. Why are objects, why are classes in certain aspects so inferior in the performance department? And to make a point that this is a real life problem, that this isn't some theoretical academical discussion. Probably all of you heard about Apache Spark, which basically is considered, let's go for a slight oversimplification, Hadoop 2.0. It's ridiculously performant, and it's written in Scala. It's running on the JVM. And there are more examples of really performant, bleeding-edge software that's written in Java. Like, out the top of my head, Cassandra, for example. The problem is that certain critical paths of those libraries have to be written in C. And that seems pretty obvious to you, I guess. It used to be the case by default pretty much 20 years ago, that the most critical paths of your Java software need to be written in C. That's not the case anymore. Huge chunks of Java used to be written in C. Not anymore. Pretty much whole of Java runs on Java. However, this is actually a very serious performance problem. And because of this specific problem, huge chunks again of Spark had to be rewritten from Scala, which is running on JVM, which doesn't support primitives over collections, had to be rewritten in C. And well, there are two sides to this problem, two main sides of why the capital L is so painful in this case. One of this is this hellish, nightmarish box, which represents autoboxing, obviously. And in production code, quite often, the same data structure going through the program gets boxed and unboxed, boxed and unboxed, boxed and unboxed, which both incurs performance penalty. It makes it less obvious what's going inside for the programmer, and it causes nullability issues, because as we know, primitives can't be null and objects can. So that's one side of the problem. And the other side of the problem is, well, how did we get here? This actually didn't used to be a problem, at least as painful as it is, autoboxing aside. Why is the problem now? So this is the second side of the coin. Basically, in the early days of Java, when the Java memory model was designed, James Gosling and the other designers, architects of the system, looked at C++, looked at the cluster flag that it was, they weighted it out, and they decided that this whole manual deallocation of memory is an insane hassle. It costs a lot of development time. It causes a lot of issues, and they were right. They decided to they decided to get rid of it. It turned out to be quite a transformative decision for the industry. We have other solutions to this problem nowadays. For example, Rust delivers them, but a lot of languages nowadays use garbage collection. And the fact that that wasn't a problem, that we abandoned the stack for the heap, was mainly to this fact. It's mainly to the fact that the CPU architecture 20-something years ago was vastly different than it is today. And even when you look at those numbers, the one on the left side represents a simple arithmetic operation, while the one on the right side represents a memory fetch. This isn't exactly true, it's simply the same order of magnitude. It's not exactly 1-to-1, but that's the order of magnitude it actually was. Nowadays it seems ridiculous, because nowadays it's, well, 3 orders of magnitudes of a difference, because the CPU architecture evolved so far, because we have ridiculous caching capabilities, and we have ridiculous branch prediction algorithms that basically contain a small swine in the processor, and they sacrifice it to Satan every time they try to predict how the algorithm will go. And that's a huge difference. Basically, originally, if you had a loop, and in that loop you had to do a fetch and 5 simple operations, the fetch was basically free. Okay, so we have to do a memory fetch, which costs us as much as any of the simple operations. We've got 5 of those, so worst case scenario, we lose 20%. Probably we do some other more complicated operations and I/O wait time, so we don't notice the memory fetch at all. Nowadays, if you've got 5 simple operations, and you have to do a memory fetch because you get a cache miss. Then, okay, you've got 5 simple operations, and then an operation that takes us 1,000 more time than those 5 simple operations, and that makes your instructions in the loop run 200 times slower. And then comes the next run of the loop, and it misses the cache again. And you waste 200 times more time again. And that's all because of the underlying architecture of the CPUs that changed. So that is a problem. That is the problem. The problem are objects. And we'll go into more details with this. Firstly, though, we need to ask ourselves this painful question. This is a very common recruitment question, as some of you probably experienced by now. And the answer is not that, it's actually kind of convoluted and not that obvious as it might seem, as it is in other programming languages. So, because as every good programmer, I'm lazy. Maybe someone would like to do the work for me and explain what's the answer to this one. Okay, time's up. Basically, the simple, technically correct answer is pass by value. There is no pass by reference in Java. The problem is that the value, well, in case of primitives, is simple. When you assign 7 to A, then you assign the value, specifically 7, to the variable A. If you assign 8 to the same variable, and so on. However, if you assign an object, then you still assign the value. But what is the value of an object in Java? It's the address where the object resides in space, in memory, which is called in Java, to make this answer complicated, a reference. So when you pass an object, you pass the value of the reference. But that is not the same as passing a reference in C. If you pass this is important for the next part of the presentation. If you pass a reference in Java to a method, and you then reassign it, like initialize a new object and assign it to the same reference, the scope ends. The scope of the function ends, and the scope in code that executed this function doesn't see the fact that you swapped the variable. If you wrote any code in Java, the technical terms of this definition might be convoluted to you, but you should instinctively understand the rest of the presentation nonetheless. So, let's consider a very, very simple class. Point which contains the private fields that are primitives of type int, x, and y. And now let us consider that if we were architecting a programming language naively, not knowing any specifics of said programming language, and we were trying to squeeze this data structure of numerous points in an array in the most performant way, we would probably do something like this. This is very, very C-like, I realize, but it is nonetheless the most efficient way of doing so. We would basically create a header in memory where we know where the data structure begins, and then we would simply start start putting after that the values of the points one by one in memory, and that way we would take up, if we had 8 points, we would take up 8 times 2, 16 memory cells for the values themselves, and 1 memory cell for the header itself of the data structure. I'm intentionally not using bytes. It's simply an arbitral unit of memory. That's how we would design it, probably. How it really looks, though, currently, as it stands in Java. If we were to implement an array of points, then we would still have the header of the data structure itself. However, what are really arrays in Java? Think about it, especially when you are writing a matrix, which you shouldn't do really at all, because you should use lists or other collections, but that's beside the point. Speaking of points, the array of so-called points really consists of references to points that are scattered somewhere in the heap. This is intentionally chaotic to give you the impression that the JVM doesn't really give you no guarantee that this is going to be squeezed in some organized, nice manner. Think about this from the perspective of the CPU. In this scenario, the CPU notices that you're working on this data set. It loads this data set into one of its numerous caches, and any time you want to query something, you're working your way through this data, it basically looks to the cache. And here comes the CPU, and it's not really as chaotic as it's here, but it does give you some impression. Here comes the CPU, and it's like, what the hell am I supposed to do with this? How am I supposed to cache this? Well, I know that I'm going to need those references, but for me, there's no correlation between this and this. How the guy is going to need this, the developer is going to need this in a moment, but I have no way of knowing that. So each time I need to actually query that data one at a time. Well, not each time, but this causes cache misses, and it causes them frequently, and as we already mentioned, cache misses are very painful. But it gets worse, because, well, as you know, arrays in Java can be of irregular size. One row can have a different amounts of columns than another row. And why is that? Because again, a matrix in Java isn't really a matrix in the sense that you would envision it here. It's not a matrix of n columns and rows. It's a matrix of n rows which have references in turn to other arrays, which you have to initialize manually, which again create more headers. Because one thing that I didn't put your attention to is that here each point has its own header. So not only in memory it's all spread out, but it actually requires more memory than here, where we have only one header for the whole structure. If we have 10,000 points, we have still one header. Here, if we have 10,000 points, we have 10,000 points plus one headers, which all take up space in memory. And it gets worse with a matrix. It's again headers of headers and so on. I'm not going to do an example, a similar example without how a matrix looks in Java. Consider this your homework, if you will. But I hope you get the general point. Again, pun intended. Well, this is a serious problem, right? How can we actually solve it? And this is where we get back to the original question: design versus performance, because there is actually a workaround to it. It's nightmarish, as you can see. It produces very brittle, unmaintainable code, but it works. And 97% of the time, when you ask yourself, should you do it like this, the correct answer is no. No way in hell. But we do it anyway, in situations where we should. We waste time about thinking about it. We do it in situations where we shouldn't. We don't do it in situations where we should. And sometimes we do it in situations when we should, and we often fuck up. We make mistakes. Because basically what you should do is, you should create a separate array of primitives of type int for x. You should create a separate array of primitives of type int that we shall call y, and you should manually proing CPUs make mistakes. We make off-by-one mistakes all the time, and this fails all the time, and still we have to write this code. There are situations where we have to write this code, and I'm pretty certain that quite a few of you guys wrote this exact same case already in a production system, probably more than once. So, if those dreadful objects are so dreadful indeed, and if they take so much space, and if they are so unperformant, and if they require the garbage collector, and if they require time and resources to allocate, and so on, the complaints just keep going. Why do we use them? Is it all a legacy? Is it all a mistake that someone made a quarter of a century ago while designing the language? And it's not that simple, of course. Basically, this whole industry should be called not information technology or something. It should be called, I guess, trade-offology, because the trade-offs never stop coming. So I complained. So let's try to answer ourselves. What do stateful objects with identity, where identity is given to us by the address in memory that an object occupies, give us? Well, they give us identity itself. We will get into that in a moment. It gives us methods. Hey, methods are awesome, right? Methods on a data structure are very pleasant to work with. Just take a procedure. If that doesn't convince you, take a procedural programming language and see if you don't find them lacking. Mutability is actually much more controversial, and probably some of you guys are already thinking that something's wrong about this chart, but we're going to get there. Nullability is even more controversial still than mutability, and again, we're going to get there in a moment. But encapsulation is not. Encapsulation is awesome, especially when you work on complex enterprise solutions where you need to isolate your code from your work colleague 3 desks over. Polymorphism is mostly awesome. It's a great abstraction, and great doesn't really do it justice, doesn't deliver it. However, again, probably some of you see something off about the types of of polymorphism I listed, because everybody loves interfaces, subclasses and superclasses not so much, and specialization is basically generics in the case of Java, which by design are awesome. Maybe it's like the current implementation, but the abstraction they provide is enormously powerful. So, as might be obvious, again, trade-offs. It's not not everything as it seems, because what seemed like a great idea over 2 decades ago, mainly mutability, seems more often than not a terrible idea nowadays. And that's because, again, the architecture of the hardware changed. That's beneath the platform. And that's a problem because we actually write concurrent code nowadays. And not only we write concurrent code nowadays, we have to write concurrent code quite often. And the levels of concurrency just keep growing. The complexity of it keeps expanding. And mutability detests, hates concurrency, and concurrency detests, hates mutability. So we should minimize it, eliminate as much as possible. But that's easier said than done, because mutability is also quite powerful. At certain situations, it's very efficient, and at certain situations, it's impossible not to use mutability. Even your beloved pure functional languages, even your Haskell, use mutability under the sheets. If they don't allow you to write mutable code, then they themselves, in their libraries, use it, at least in their data structures. So mutability goes both ways. It's both a pro and a con, more of a con, but still there are situations when it's validated. Nullability is basically only a con nowadays. There's only one really good argument, especially since we got optional. Then there's really only one good argument for using null at all in your code, and that's because optional comes at the performance cost. But basically the irony of this is that Valhalla, which I'm going to get into more detail in a moment, eliminates that cost. So objects nullability has a very slight advantage in performance, so that's an advantage of objects, but Valhalla removes that disadvantage, so it stops being an advantage of objects. So nullability is 100% a disadvantage. And to prove the point, there are actually programming languages nowadays that don't have the concept of null at all, because it's actually, it requires a different mindset, but you can do without null at all. It's possible. There is this famous article that I recommend you to read, The $1 billion Mistake. That's the title of it, and it's entirely about why the idea of null was so terrible. Easy to implement, terrible consequence. And as I mentioned, there are edge cases when you need identity. And I'm going to talk about them in a second. There are edge cases where you need mutability. I think we are over the discussion of inheritance. There's not much people really defending inheritance nowadays. I'm a Java developer, but let's just admit that that ship sank, and there's no point defending it anymore. That was simply a mistake. But interfaces and generics are awesome. What do objects give us in some circumstances over primitives? They give us identity in a moment. They give us awesome in certain situations, not often, but sometimes awesome. They give us methods, awesome all around, very nice designs and enabled by having fields and methods in a data structure. They give us encapsulation, awesome. And they give us interfaces, awesome, and generics, awesome idea, less than awesome implementation. At a terrible cost. Because as you saw in the example a few months ago, the data structures in those arrays that I presented were very sparse. They were they don't really work hand in hand with modern CPUs. And in consequence of the above fact, it forces manual specialization. What that is, I will get into in a moment. And again, identity mutability is kind of a double-edged sword. In certain contexts, it's an advantage. In certain contexts, it's a disadvantage. And nullability is always a disadvantage. So identity. I'm not going to force you to make a show of hands, because some clever math aside, 2 equals 2. Okay. In almost all contexts where this is valid question asked for an engineer and not a math professor. If you have a number 2 and you have it in your left hand and a number 2 in your right hand, you have the same amount of something in both your hands. So in this particular example, identity is completely unimportant. It doesn't matter if I have a 2 called A, and if I have 2 called B. A equals B, and it might be as well called a zebra, for all I care. The value is the value of 2 is in its value. Okay, so that's simple. We don't care about identity at all in this case. So we don't need this to be an object, right? Because all we care is if 2 has the same value. If we have 2 on one hand and 3 on the other hand, that's clearly something different. Okay, so do we care about identity in this case? And this is an honest question now. Who thinks that if we have 2 guys like that, if they are identical? Show of hands, if I may ask. If those two objects are identical, okay? So who thinks that they aren't necessarily identical? Okay, more hands. Okay, so what happens now? Let's assume they are identical. Now we added the bank account. This was, of course, is a very, very oversimplified example, but let's assume we have an object like that. Okay? If they were identical here, then I guess they are equally identical over here, right? So now let's assume we have a guy that's named John Smith H24, and a different guy who's named John Smith 24 in real life. That's not exactly something that seems very unreasonable, right? And let's assume that the guy, they both went to work now for the first time in their lives. And the first guy simply happens to work in, I don't know, McDonald's, whatever, Python. Let's hate him Python a bit. And he got $1,000. And the other guy happens to be lucky and happens to be the son of a CEO that just got $1 million for signing a contract with his own dad. I guess it's kind of important that we transfer the money to the right person, right? Of course, we could do that elsewhere by adding a bank account or holding the data in a different object and so on and so forth. But this is just an example to give you an idea. It's rather important that the right person gets the money, the proper amount of money, despite having the same name and surname and age. So so identity is kind of important, and we better store that information in an object in this case. So the question, is identity good or evil, is of course, as it always is in IT, it depends. And going back to the question of mutability, which I already went in some depth, Whether mutability is good or evil, well, the answer to this one is actually not it depends, but it is a necessary evil in some circumstances. There are situations where I don't know what you will do and how pure functional you write your code. Mutability gives you a win, at least in the performance department. And there needs to be some state in your application if your system is complex enough. There are simply, the reality is mutable. The reality around us is mutable. We can model it immutable very often, but not always. We have to store the state somewhere. The best place to store it is not in your application, preferably in someone else's application or in a database, but you have to store it somewhere, and sometimes it's your application. So we can't escape mutability, and again, we need objects for a good abstraction of that. So despite all the disadvantages, there are situations where you simply have no other way. As far as manual specialization goes, we have, again, generics to thank for this one, and their lack of support of primitives, because, as we already mentioned, some operations on primitives are far more performant than the same operations on objects. And because of this requirement, there's a lot of classes in the Java standard libraries that look like this. I think there's actually optional integer, optional long, double, and that might be it, but I might be mistaken here. I didn't use them for a long time. And the same goes for string. The reason this exists, because this would work, right? This would work. This does get the job done. The problem is this gets the job done much faster in certain workloads. And they simply had to manually write classes like that. Fun fact, in C#, because they don't have row types, when they migrated to generics without row types, they ended up with a lot of classes like list of integer, list of char. I'm making this up because I didn't refresh my C# for a long time, but they have classes like that all over the place. And what we really would like to have is not this on the left-hand side, but this on the left-hand side. We want to have streams of primitives, and we want to have optionals of primitives, but we don't want them to behave like primitives. We want them to have methods and all the goodies that go with objects, right? We want something that's as performant as this, and as powerful as this. So, well, that would be a beautiful world to live in, right? Well, we're getting there. This is a reminder of the pros and cons of objects. And what are the pros and cons of primitives themselves? This is a major point. I forgot to mention this. Garbage collection. Don't I hear everyone screaming inside now? This doesn't come for free, and this causes all manner of problems with objects. So, what do we have with primitives? We don't have methods. We don't have fields. We don't have identity. We don't have encapsulation, and we have no polymorphism at all. Primitives can't implement interfaces. Primitives can't even implement a simple interface because they have no methods. They are far less pleasant to work with in terms of creating abstractions and designs. So why would we use them? Why does Java even have primitives, right? Because of performance. It was a necessity to implement them 25 years ago, and it's much, much, much more necessary nowadays. So, again, wouldn't it be nice to take the advantages of both worlds, mash them together, and get on with that? Start using that miraculous baby of primitives and objects. Well, obviously, this is IT, so it probably doesn't exist because it would kill off a lot of trade-offs. And surprise, surprise, it actually does. It's called value types, and a lot of languages have it nowadays. That's probably after we've got lambdas, and since we have modularization, this is the most glaring lack of a feature in the Java language. When we get this, well, there is no next major pain point from my perspective. Everything is smaller in terms of the pain department for a developer than value types that remains in the backlog. If there was an advertisement slogan for value types, it would probably be, and this is semi-official actually, codes like a class, works, behaves like a primitive. And we'll get to that. A different slogan, and now you should realize why I don't work in marketing on a daily basis, because I'm terrible at this, is more performant classes with restrictions. Alternatively, user-defined primitives with bonuses. So it's kind of halfway, but not quite. It has more of the advantages of both than disadvantages. And again, we get back to our oversimplified example. That's a point class, whatever, written a million of those. And this is actually all it takes to write a value class. And you actually, there is a prototype, you can download it, you can compile it, and you can start writing code like this. And what do we get by that? Well, we'll get there in a moment. I just wanted to give you a sneak peek of something else. We are getting data classes, also in the nearby future. And what that means in practice is you don't have to write those 3 dots. And by 3 dots, we mean obviously toString equals hash code, compare, all the boilerplate that the IDE handles for you is taken care of here. And that's separate of value types. It's just a bonus. It works nicely together, that's all. That's how you will be defining simple POJOs, amebic classes in the near future. That's just a sneak peek. So you instantiate them ridiculously easy, right? All the work, all the magic is happening in the JVM. You don't need to know how does it work underneath the sheets. It's taken years. It's extremely complex to implement, mostly because of its interactions with generics. But what is the main difference? What does it really bring to the table? What do we win this way? Why am I making this huge introduction? Well, for you to better appreciate the benefits, I hope. Basically, think of data value types as primitives that are stored on the stack, as primitives are, that don't require garbage collection, as primitives don't, because of being on the stack, which are efficiently squeezed together in memory, as the table as the RI I showed you previously for primitives is, as the one you would write yourselves if you were to do so. They don't require allocation because they don't require deallocation either for the same reasons. They have methods as objects do. You basically write an object. You basically write a class. You simply write 4 more layers that it's a value class and not an ordinary class, and that sends an information to the JVM that it should treat it performance-wise like a primitive. And the JVM is able to do that because we sacrifice two things in return. We sacrifice identity and we sacrifice mutability. And mutability is easy to sacrifice. 95% of the cases, you don't need it. Identity is also actually quite easy, not as easy. You sometimes need it, but in the majority of cases you don't. So what happens now? Basically, if you need identity or mutability for some reasons, you still use objects. But that's the minority of your use cases. If you don't, for stupid data classes, which probably are the vast majority of the objects you create during the lifetime of the application, value types is all you need. You get interfaces and specializations. You don't get subclasses, but those suck. You get encapsulation, which is awesome. You get methods, including private methods, which is awesome. You get non-nullability. It enforces non-nullability on you, which again is actually an advantage, because null sucks for all purposes other than performance, because it creates an object. But it doesn't anymore, because value types don't create objects. And in fact, optional will become a value type, which means it will be for free. An optional will contain only one piece of information, whether or not it has an object and where that object is in memory. And that's because it's going to be rewritten as a value type. So basically, again, the takeaway from this is, whether I need identity or mutability, probably not, then use a value type. If I do, which is perfectly fine, then keep using objects. The question that might arise in your heads is, what happens with primitive types? Well, the cleanest design would be, and that's actually what happened, they are all going to be re-implemented as value types. Which means, this is the big part, value types work with generics. So, hello list of int. Goodbye optional of long. Just a quick reminder. So that's the big takeaway. But there is something this enables as well. A few small things. Who has written code like this ever in their life? A pair, a tuple of something. Well, probably, yeah, that's what I thought. Probably dozens of times, right? Well, there isn't such a class in the JVM, in the Java libraries, and there's a reason for that. Two reasons, in fact. The first reason is because they are waiting for value types, and they don't want to put trash in the library that no one is going to use after they put in value types. And the second part is, you should really use a domain object for this, because of semantic reasons. And if you think you shouldn't, then think again, and because you're probably wrong. If you still think so, then still think again, and maybe you're right. But there are cases when you actually do need that. There isn't, as we already mentioned, there isn't such a class in the Java libraries. So this is an example from VAV, which I recommend you full-heartedly. It's an amazing extension in the Java language. And just look how it sucks, because this class is generated. You can have a tuple of 8, and then you query, as you can see by the underscore, for generated fields. And it, of course, is an object itself, so we create even more objects. The syntax is terrible, but it's the best we can have. But it's the best we have in this regard, currently. And it gets worse, because, as I said, we can have a tuple of n, and it can be of varying types. And, well, imagine yourselves a tuple of 7 of the varying types and making all those assignments. Well, you don't have to imagine, probably you saw stuff like that already. So where are we going, and where are we going thanks to value types? Two things. Tuples supported by the language, and multiple return, also thanks to value types under the sheets. So I can return two strings at the same time, which is in the signature, and I can then assign both of them at the same time through one execution of a method. If I didn't need one of them, all I had to do is like, it's going to, I think it might even be already the case in lambdas, you can use an underscore. So if I was only interested in the first name, I could write string name, comma, underscore, equals function.
How do you use those in method parameters?
How do you use those in method parameters? The answer is that I don't know, because no one does. They haven't settled on the syntax yet. User-defined primitives. So we will get primitives become value types, but it doesn't end at that. You can create your own primitives like, well, the obvious answer is 128-bit numbers, like unsigned numbers, like numbers that can have a value from 0 to 100, I don't know, age, whatever, like temperature that begins at 0 Kelvin in Celsius, like only valid geographical coordinates. You can have data types like that, which are primitives, which are very efficient, and which you don't have to test. You don't have to test if the user put in valid input, because he can't, because the data type itself doesn't allow him that, him or her. So that's one thing. Okay, canonical monads. I'm wrapping it up now. Some of you might know this quote. Well, it's okay. Value types give canonical monads. What are canonical monads, you might ask? Well, that's an obvious question, right? Come on. A monad is just X. A monad in X is just a monoid in the category of endofunctors. What's the problem? And that's a famous quote. Of course, I put it out of context, because all told, a monad in X is just a monoid in the category of endofunctors of X, with product X replaced by composition of endofunctors and unit set by the identity endofunctor. Again, what's the problem? It's all perfectly obvious now. That's a quote from the Incomplete and Mostly Wrong History of Programming Languages. If you didn't get that, come on, dudes, get a hold of yourself. This should make it perfectly obvious. But seriously, though, optional is an example of something that is a monad, should be a monad. It's not really currently. The point is that thanks to the value types, it's going to be more powerful and more efficient. And lastly, but not least, well, lastly and leastly, I guess, I started with that. I mentioned it a few times, but this is the very, very important part. There are three things that are wrong with generics in Java, and generics are probably the most important thing we ever got in the language, even including lambdas. Raw types, and that's unfixable. That was a design choice they made for migration reasons. That's a serious problem. We can't do anything with it. We have to simply live with it. The second problem is that we have definition side generics, not use side generics, not definition side generics. Not going into specific, that causes a lot of mess with wildcards and whatnot, where the mess is much harder to deal with at the user space. This is going to be fixed soon by a separate JEP, so that's nice. We've got one out of the two major problems down. And the third problem is that you cannot generify over primitives. And that's by far the most important one from my perspective. And value types fix that. So we're down to raw types, which suck, but I guess we can live with that. Questions? Thank you very much.